like v equals a sine omega t or y equals a sine x. Y and x are the common symbols to use for variables in a function, y and x. And if I were to plot a graph, you're used to seeing y on the vertical axis and x on the horizontal axis. And the graph plotting software that you're going to use, Autograph, only recognizes these values of y and x. So if I want to plot other variables like v and theta in this example here, then I have to assign x to say theta and y to say v. So I'm going to plot y equals a sine x. So I go to Autograph and type into the equation button, which is this button here, the equation which is y equals, literally type it in, a sine x. It doesn't recognize capital A, it only recognizes lowercase letters, so we won't be able to put in capital A. Hit OK, and it plots the wave here. I can plot it in degrees or radians, and if you look at this button here, this is the degrees button, and this is the radians button here. So if I were to, let's stick to radians for now, I can drag this thing around. If you go to this button, which is the hand tool, I can drag the scale around, which is quite nice. So I'm only interested in this particular case, what's going on the right-hand side of this point here. This is almost always time. And so often in an engineering situation, we're only interested in what happens after time 0, time starts to go. So we're only interested in this part of the graph. Not always, but usually. So dragging the graph over so this is far over on the left-hand side is usually a good thing to do. And then we can do other things with this thing. We can expand. Sort myself out here. I can now zoom in on this thing. I can change the axis. I can zoom in on the x-axis, which is this button. I can zoom in on the y. Sorry, zoom out on the x, zoom in on the y, zoom out on the y. And they're fairly self-explanatory, these buttons. So if I were to zoom out on the x, for example, it stretches out the x-axis, which means we get more waves. If I zoom in on it, then I zoom in on the x-axis. Similarly for the y-axis. If I zoom in on the y-axis, then it stretches the wave out. It zooms in on the y-axis. In other words, the y scale is now a smaller scale as opposed to a larger scale if I zoom out. I can also zoom in on a particular part, which is this zoom box. So you click and drag a box around a particularly interesting part of the script. So if I was interested in this bit of it, where it crosses the axis here, I would zoom in and put a box around that bit, and I can zoom in on that part of the scale and read off the time, if this was time, at which it passes that point. If I play around with it and I want to, I've decided I want to go back to the start, hit default scales, and it goes back to the default point. Now let's look at it. Let's look at one oscillation of this wave and relate it to what we've been talking about before. So if I just copy this particular thing and put it into here, and we look at it and relate it to a rotation. And we talked about this last time, of a circle. Set of axes, and then we allow this thing to rotate around, something that rotates about 0. Some vector rotates about 0 in the anti-clockwise direction, angular velocity in other words. At time 0, or at angle 0, it's along the horizontal axis. And so the angle is 0, and we start our wave at 0. So the 0 point on here corresponds to the 0 on the x-axis. And as this thing rotates around here, so as I come round here, I go up here until at this point I reach the maximum. And then I carry on going round till I hit the x-axis again, and it comes down and hits the x-axis. So after a half a turn, I've got to the x-axis. What's a half a turn in radians? Pi, and here it is, pi. Okay, you might not be able to see it from the back, but that's the pi. So after one complete turn, we get to 2 pi. So 2 pi radians is one complete turn, and that's what's that's what this graph looks like. So what this has plotted is y equals sine x, and notice the high point. It's at 1. So in other words, that's telling me this point here is 1. In other words, the length of the radius is 1. The size of the vector that's causing this rotation is length 1. If I want to change that, I change the amplitude. This is the amplitude of the wave, isn't it? And so if I want to change the amplitude, what I'm actually doing is changing the size of this rotating vector. If we go back to autograph, I typed in y equals a sine x. I can change the value of a, which is this button here, that one. So any letter I put in this equation, apart from y and x, are taken to be constants. So as soon as I put another letter in, like say a, that will appear in my list of constants. At the moment there's only one constant, so a is the only constant. If there was more than one constant in there, this would expand down and I'd have a series of all the letters that I've assigned. And it by default set a as 1. If I change the value of a, what will happen to this wave? Sorry? Go higher, right. It won't peak at 1, it will peak at whatever value this is. So if I change it to 2, then I find it peaks at 2. If I just drag this down a bit so you can see it, you can see that it peaks at 2. So in other words, if I plot y equals 2 sine x, then the 2 represents the amplitude, the peak of the wave. If I look at the wave again now, go back to here and put in some sort of, I need to just get rid of that, put in a letter inside here. So I want to plot y equals a sine brackets bx, those brackets. I put a bracket around the bx because I want it to give me the sign of that whole thing, bx. Hit OK. And now, by default, it says b is 1, so it's not changed at the moment. If I change b, note the effect on the wave. So now I'm going to change b and increase it to 2. Now look at the wave. Let me just zoom out a bit on it so that you can see the whole wave. Let's focus in on just the bit I'm interested in, which is this bit here. Let's put that into the notes. It's all very technical. So now we can look at this and I can actually write on here what I've plotted. Y equals 2 sine 2x. Right, Chris. Look at this wave. This is y equals 2 sine 2x. Look at the one we've just done. And that's the wave y equals sine x. So in this case, a was 1 and the number in front of here was 1. What's the difference between this wave and this wave? I've actually not copied enough of this wave. Let's go back to autograph again. And just that's what I wanted. Look at this. You can see within the fraction, the time of 2 pi, within that angle of 2 pi, I've actually now got 2 waves rather than 1. So if I've got a 2 in there, it means I've got 2 waves within the space of 2 pi. I've doubled the rate at which this thing is rotating. If I go back to my notes here, so the 2 represents the rate at which this thing's rotating here. That's a particular speed, and if I increase it to 2, it's rotating more quickly because I'm getting more waves within that period of time of 2 pi. So therefore, the number inside here, this number here, represents the angular velocity, the rate at which it's rotating. And if I increased it to 3, I would have 3 waves within the angle of 2 pi, and so on, within 2 pi along the x-axis. The assignment asks you just to study that. And if you look at the textbook, the question on sine and cosine and waves, trigonometry, I think, is the title of the chapter. It talks about this, but I wanted to just introduce the idea and show you autograph for the first time that you can use to plot it. So as part of your work towards assignment 2, I'm now going to issue assignment 2, you need to just look at that section on trigonometry, on sine and cosine waves, to be able to plot the waves that you're asked to do in the assignment. Page 204 in the textbook, trigonometric waveforms, it talks about this in there, so you can read it. It shows you the sine wave, the cosine wave, which is related, but instead of it starting it along the horizontal axis, it starts in the vertical position. So it starts here rather than at 0. But if you look at it, it talks about these 3 waves, the sine, the cosine, and the tangent, and talks about what happens if you increase or decrease the value of the numbers inside the wave function. Okay, so read that section, and then assignment 2 asks you to draw out, to sketch some wave functions, which you can do either by hand, or if you want to, you could try putting the numbers into autograph and getting autograph to plot it for you using the computers up in the LRC.